All right, welcome to the next video. Unit 1 is done. So now we get to get into the fun stuff. All right, Unit 2 begins today. It's kind of interesting. The title for this unit, I guess you could call that atomic structure, but also atomic structure specifically is sort of the subject for today. So atomic structure is something that's going to take us quite a long time to completely understand, and in fact scientists today don't even completely understand it, funny enough, but we're going to be learning plenty about it, so there will be different titles for lessons in the future, but today we're just going to go with atomic structure. The objectives for today, at the end of today's video, you're going to be able to classify subatomic particles in an atom according to their properties. And you're also going to be able to determine the number of those particles, okay, so the number of protons, neutrons, and electrons of an isotope based on either its name or nuclear symbol. So we're going to be getting into all that here in just a few minutes. Before we start talking about atoms and subatomic particles, though, okay, I want to do a thought experiment. So I really want you to do this at home. I'm going to do it here with you. So let me actually go ahead and grab my piece of paper. Got a little notebook here. So please go ahead and do this right now. If you need to pause the video, go ahead. But I need everybody to find a small piece of paper. Okay, it doesn't need to be a full-size piece of paper because we don't really want to waste paper, and we're going to be destroying this piece of paper. So it can just be a small piece of notebook paper. That'll be fine. I'm trying to take the little frilly things off of this, and it's not cooperating. But it'll be okay. All right, so while I'm getting this ready and while you're finding your piece of paper, let's read the directions here. So we're going to do a thought experiment. Find a small piece of paper, tear it in half, toss one half aside, but hold on to one of the halves. Okay, so I'm going to fold my piece of paper in half. I'm going to crease it a few times here, just so that it rips kind of nicely. And then I'm going to tear it in half in just a second here. Okay, so I'll tear mine in half. Like I said, take one half and throw it away, or get rid of it. Toss it aside, but hold on to the other half. You are going to repeat this process, okay? Over and over and over again, all right? And I'm going to actually do it. I'm probably not going to do it as many times as you are because, you know, I don't want the video to be, 45 minutes or anything like that, but just repeat this process over and over again. Okay, so I'm gonna tear it again. So now I have like a fourth of what I started with. Take this piece, fold this in half, and as you're doing this, okay, now I have an eighth of what I started with. As you're doing this, as you're repeating this process, I want you to ask yourself the question there that you can read in the second paragraph there. Could you, given the right tools, keep doing this forever? Obviously, our fingers can only, work with things that are so small, right? If eventually this piece of paper is going to get too small to where my fingers are not an effective tool for folding or ripping, right? You can see I'm already getting relatively small here, and in just a few tears, it's going to be too small for me to work with. But that's not what the question's asking, right? The question's asking, could you, given the right tools, okay, even if they have to be imaginary tools, right, things that don't necessarily exist, could you keep doing this over and over again? Could you keep going forever? Could you infinitely rip this in half? Or would you be forced, that should say forced, would you be forced to stop at some point? Okay, and then why or why not, right? So think about this to yourself. Totally okay if people have different answers. In class, we would actually sit here and do this. It's kind of fun, other than the part where I have to clean up scraps of paper because people aren't good at cleaning up after themselves. So now that part's on you now. So yeah, what do you guys think? Is this something that you could keep doing forever or not? Well, some people might say, sure, you can keep doing it forever. If you have the right tools, you could just keep going, right? Why not? Other people might have the opinion, and see, at this point I kind of have to stop because my piece of paper is too small. Other people might say, well, no, that doesn't make any sense. You can't just go forever, right? Like, surely there is a smallest thing that you can't tear in half. So those are sort of the two sides of the coin there, right? You're either in the you can go forever camp or you can't. And it turns out that there kind of is a right answer. And the reason that we're talking about this is because this directly applies to, what I was just talking about before, atoms, right? We were just talking about on the previous slide how we're going to be learning about atoms and subatomic particles. So let me tell you a little bit about this guy named Democritus. Okay, this is a Greek philosopher from like ancient Greece, so BC, several thousand years ago. I don't remember the exact dates, and that doesn't matter. But this guy, Democritus, is credited with coming up with the first concept of an atom. Okay? And let me tell you a little bit about his reasoning. Right? So let me go back to the thought experiment here. He thought to himself, he thought about this question, right? Could I keep breaking matter in half and just keep going and keep going and keep going? Could I keep doing that forever? And his explanation, right? He was a philosopher, right? So he gets real fancy with his ideas. His explanation for why you couldn't was that it doesn't make sense to be able to do it infinitely many times, right? An infinite number of times would mean you would literally never stop, right? He didn't think that made any sense. Like, in his brain, he thought, surely you can't just keep cutting it in half forever, like infinitely over and over again. There must be a point at which you get to a substance or to some object that can't break in half. That was his explanation. And it turns out that he was partially right, okay? He is credited with coming up with the first concept of an atom, which we recognize as being sort of the basic building blocks of our universe. And while he was never able to prove it, okay, he wasn't a scientist necessarily, he was more of a philosopher, he wasn't able to prove that these atoms exist. It is important that we acknowledge the fact that the idea of an atom dates back for thousands of years. And in fact, the word atom comes from a Greek word, atomos, which means indivisible. Now, it turns out that actually you can break atoms in half. Okay, we figured that out, and by we I mean humans figured that out like 100 years ago, right? Not that long ago, actually, in the grand scheme of things. You can break atoms apart, and when you do, you release immense amounts of energy, right? And that's called like a nuclear reaction, right? So like a nuclear bomb works off of the fact that you can split atoms apart and release the energy within there. So he wasn't completely right. But he sort of got the process started in terms of talking about what the universe is made of at a fundamental level. Now, we are going to fast forward by about 3,000 years, okay? So we are not going to spend a whole lot of time in this class this year talking about the history of atomic models, okay? There's people that are important like John Dalton, like J.J. Thomson, like this guy, Ernest Rutherford. Okay, we're going to talk a little bit about his model here in a second. We're not going to go through all the nitty-gritty details for a couple of reasons. One, we don't have time. Two, it's not a history class. I think talking about them is useful and can be illuminating, especially the experiments that they did to find out what they found out. That can be pretty interesting. So if you are interested, you should look into J.J. Thomson discovering the electron and Ernest Rutherford discovering the nucleus. But we're not going to get into it in my class, okay? And you're not going to be assessed over the history of atomic models, okay? So this is what we're going to work with, right? We're just going to sort of fast forward till about 1900, and that is when a guy named Ernest Rutherford discovered basically the sort of modern model of what an atom really looks like. Not exactly. There's still some fine details that we're going to get to in the future. But what he discovered is that atoms are made up of three different things, okay? The protons and the neutrons are big, relatively, and are located in the center of every atom. Together, the protons and the neutrons make up what is called the nucleus. The nucleus of an atom is not some sort of special container or anything like that. It's not some different object. It's just what we call the protons and neutrons together, okay? So you could theoretically have an atom that has a nucleus that is only one proton, and that does exist. We're going to see that in just a few minutes. And then we also have these electrons, okay? And the electrons are sort of zipping around on the outside of the atom. I shouldn't say zipping around. The behavior of electrons is really peculiar and strange. We're going to spend some time learning about electrons in a few weeks from now. But yeah, I mean, this is essentially what atoms look like if you could see them with your naked eye. The one thing I will say is that this is not drawn to scale, okay? So the electrons in reality are much, much, much smaller than the protons and the neutrons, so they wouldn't quite be this size. And also these like loopy things, right, that you recognize from like the Jimmy Neutron logo, these loopy things aren't actually there. There's no like lines that, you know, the electron is holding on to. In reality, the electrons just sort of exist outside of the nucleus and don't even necessarily travel in orbits like this, but we're going to talk about that later. Okay, those three subatomic particles, protons, neutrons, and electrons, make up every atom in the universe. Okay? So while the universe is made of lots of different elements, right? Hydrogen, helium, lithium, beryllium, boron, and so forth, gold, silver, copper, iron. Every atom of every element is only made of the same three things. And it's the number of these different particles in each atom that determine which element it is. Okay? So this right here is what the entire universe is made of. Well, this right here constitutes all matter in the universe. Okay, there's other aspects of the universe that we're not going to get into in this class, but all the atoms in the entire universe are made of these three things: protons, neutrons, and electrons. Like I said before, protons and neutrons can be found in the nucleus, in the center of every atom. Protons are positively charged, while electrons are negatively charged. I have the numbers +1 and -1 here to show you that the amount of positive charge in a proton is exactly equal to, but opposite, the charge of an electron. So protons and electrons kind of cancel each other out. If you had one proton and one electron, the total amount of charge there would be 0, okay? Charge is kind of like magnetism. So you're probably familiar with a magnet. You guys know that magnets have like a north pole and a south pole. Charge is kind of the same way. There's like a positive charge and a negative charge. And it really does kind of behave the same way that magnets do, right? So if you have a positively charged object and a positively charged object, those are similar charges. They actually repel away from each other. Whereas opposites, right, like a positive and a minus, opposites attract, okay? So in fact, electrons are attracted to protons, okay? What else is important here? Let's see. So the mass, I did talk a little bit about this on the previous slide, the relative sizes of these things. The protons and the neutrons, if you measure their mass in kilograms, right, so every human weighs, I don't know, about 100 kilograms or 150 kilograms, depending on how big you are, something like that. So humans weigh about 100 kilograms or 150 kilograms. Protons weigh 1.67 times 10 to the negative 17th kilograms. What this means is that you could write 0.000, okay, so 0.17 zeros and then 1673. Like, that's how many kilograms. Very, 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 very small, okay? Neutrons are essentially the same mass as protons. Electrons are even smaller, okay? So this is 9.109 times 10 to the negative 31. So that's 0.031 zeros until you get to a number, okay? So electrons are very, very small, right? They're like, you know, if you think about shrinking from human size to a proton, you almost have to do that again to get down to the size of electrons in terms of their mass. So we're not going to use these numbers that much, the kilogram masses. What we're going to do is we're going to sort of create this new unit, which is called the atomic mass unit, okay? And this is just going to make our lives way easier, all right? what we're going to say is that this amount of kilograms is basically 1 atomic mass unit, okay? And this number is very close to that, so protons and neutrons are going to have a mass of 1 in our new unit system here, 1 atomic mass unit. And electrons, because they're so small compared to protons and neutrons, we're going to give them a mass of basically 0, okay? They don't actually have 0 mass, okay? So in reality, electrons do have mass, but they're so small that we're going to just assume that their mass is basically negligible in terms of any sort of calculations that we're going to do. And then once again, the electrons can be found outside the nucleus in contrast to the protons and neutrons. Okay, when you look on the periodic table, the periodic table is a fantastic tool, by the way. Okay, so the periodic table has all the different elements in the universe, known elements in the universe. There's different pieces of information on the periodic table, and those different pieces of information can be used to tell you what atoms of those elements look like, okay, and what they have inside of them, okay? So this top number here is called the atomic number. Okay, so if you look at your periodic table, the one that I sent home with you in your resources, or if you go on a website and look at a periodic table, you're going to see a number up at the top. That number is always a whole number. Okay, so notice this is not a whole number. This number is always a whole number, and this number is called the atomic number, and every element has a different number. Okay, so every element has its own number. I know all of the elements up through like number 42. I'm not going to recite them here on the video, but in person when I see you, I'll do it, okay? The atomic number tells us something very important about elements, or about atoms of that element. The atomic number tells us how many protons an atom of that element has. Okay, so hydrogen has 1 proton because its atomic number is 1, okay? And in fact, you almost don't even want to think of it that way. You should think of it this way. If an atom has 1 proton, that is hydrogen, okay? So all atoms that have 1 proton are hydrogen, okay? And they behave a certain way due to their number of protons, okay? This is always true, okay? So the atomic number is always equal to the number of protons, okay? The number of protons in an atom determines what element that atom is. It's like its identity, okay? Think of it as like the hydrogen being its first name and number 1 being its last name, right? It's just part of who it is. In a neutral atom, neutrally charged, the number of protons is equal to the number of electrons as well. Okay, so you'll recall that on this previous slide I said that the amount of positive charge in 1 proton is equal but opposite the amount of negative charge in an electron. So if you are working with a neutral atom, lots of atoms are neutrally charged, then the number of protons is equal to the number of electrons. And let me just tie this back really quickly to the objective for today, right? Part of your objective for today is for you to be able to determine the number of protons, neutrons, and electrons in different atoms, okay? So this right here, these 2 bullet points are very important, okay? Now there do exist things called ions, which are just atoms, but these atoms have non-zero charges. And so what that means is that the protons and electrons are not equal to each other. We're not going to worry about ions today, but we're going to see them in the relatively near future, okay? Okay, you might be thinking, how do I find the number of neutrons, right? We just talked about protons and electrons. Okay, so in order to determine the number of neutrons, you have to deal with this thing called the atomic mass, or the atomic weight, okay? One other piece of information on the periodic table is a number down at the bottom of each box. This number usually has a decimal point with several decimal places after. This number right here is referred to as the atomic weight. Really, that should say atomic mass, okay? I'm always going to refer to this as the atomic mass in the future, okay? And in reality, it's actually referred to as the average atomic mass, okay? We're going to learn what the difference is between atomic mass and average atomic mass in just a few minutes, okay? But this number down here, that's got a decimal point and some decimal places, that is always going to be the average atomic mass, and we're going to learn what that means here in just a minute. Generally speaking, the mass of an atom is equal to the sum of its protons and neutrons. Okay? So go back here. Remember how we assigned the mass of a proton and the neutron to be 1 and 1. So basically all you have to do to figure out the number of neutrons, take this mass number, subtract the atomic number, right? So take this overall mass, subtract the number of protons, and that's how many neutrons there are. So how many neutrons would we expect in an atom of hydrogen? Well, on average, 0, okay? And that's because 1 minus 1 is 0. Now there's this issue with this 0.008, okay? You can't have 0.008 of a neutron. That doesn't make sense. And we're going to grapple with that here in just a minute, okay? All right. So we've learned basically the basics of what an atom looks like, protons, neutrons, and electrons. I got one last little curveball for you, okay, before I let you go for today. There are these things called isotopes, okay? Not all atoms of an element are the same, okay? So hydrogen, not all hydrogen atoms look exactly the same. There are some different versions of hydrogen. All the versions of hydrogen are going to have 1 proton, okay? But there's some other way that they can differ, okay? Isotopes of an element have the same number of protons, but a varying number of neutrons, okay? So the number of neutrons can actually vary, and that is what distinguishes these different isotopes from one another, okay? Like it says here, most elements have several different versions of themselves called isotopes. Isotopes of an element have the same number of protons, but a varying number of neutrons, okay? Generally speaking, isotopes of an element tend to behave the same way. So different isotopes of different elements usually don't alter how the element behaves, but they can differ in some way, all right? And that's because of the fact that they have a different mass, right? If you have more neutrons, you're going to weigh more than if you had less. Got a couple of examples to show you. So we've been talking about hydrogen. So these are the 3 isotopes of hydrogen, and there are only 3 naturally occurring isotopes of hydrogen. You can artificially make bigger isotopes of hydrogen, but you're not going to find them in nature. These 3 you will find in nature, okay? They're all still called hydrogen, okay? So if you look at the very bottom of the picture there, it says hydrogen 1, hydrogen 2, hydrogen 3. Those are the different names or isotope names for hydrogen. Just above that, there are what are called like common names. These are names that are sometimes used. I'm not going to use them. We're going to use the names down at the very bottom in black. But the names protium, deuterium, and tritium sometimes get used. If they're a common isotope that people see a lot, sometimes they adopt some sort of common name. All right. So let's look at the pictures here, the models, and try to glean the difference. Well, you probably spotted it, right? The only difference between these 3 isotopes is the number of neutrons, right? 1 proton, 1 proton, 1 proton, 1 electron, 1 electron, 1 electron, 0 neutrons, 1 neutron, 2 neutrons. That is the difference, okay? It's just the number of neutrons. What that means, okay, is that this atom over here actually weighs like triple what this one does. Okay, and this one would weigh like double what this one does, right? The mass of this one is 1 proton plus 1 neutron, so a mass of 2. That's double than the mass of this one, right, which would just be 1. I want to tell you something interesting about the isotopes of hydrogen, okay? Usually, isotopes of an element don't really differ in terms of their properties, like how they behave, right? But with hydrogen, there actually is a pretty big difference. And this is because of that weight difference, or that mass difference, right? Hydrogen 1 has a mass of 1. Hydrogen 2 has a mass of 2. This is double the mass, right? Water is H2O, right? 2 hydrogens and 1 oxygen, okay? So let's say you had water that was made of hydrogen that looked like this, okay? Well, that's going to be most water, okay? Because in fact, of all the hydrogen in the universe, like 99.9% of all hydrogen in the universe is hydrogen 1, okay? So it all, for the most part, hydrogen looks like this, right? 99.9%. However, there is some hydrogen out there that looks like this, right? That's hydrogen 2. So let's say you had some water that was made with this hydrogen instead of this hydrogen. That water would have a higher mass, right? It would literally weigh more than this water does. And in fact, you can make that type of water, and it's called heavy water. You can Google it, okay? It really does exist. Sometimes it's called D2O for deuterium-2, and then the one oxygen. If you were to drink heavy water, like if you were to drink like half a liter of heavy water, you would get sick and potentially die because your body is not used to how the hydrogens in heavy water behave. It's used to how the hydrogens in regular water behave. Well, just how hydrogen in general behaves, right? Regular hydrogen. Your body is not equipped to deal with massive amounts of deuterium, of hydrogen 2. Your body is perfectly capable of dealing with this. It does it every day. And in fact, your body probably does encounter hydrogen 2 every once in a while. But if you flood your body with D2O, or with deuterium, with hydrogen 2, you can get very sick and potentially even die. So that's just an interesting thing about isotopes. Okay, I got 2 final slides and then I'll be letting you guys go. Isotope names, so the names of different isotopes are really, really easy, okay? All you need to do is list the name of the element and then a dash or a hyphen and then its mass number, or how much it weighs, its mass, right? So some examples, hydrogen 1, helium 4, right? So these down here, the names in black, those are the isotope names. There are also isotope symbols, which are sometimes called nuclear symbols. These you'll see a lot more often than the actual isotope name itself, right? So you'll see this type of thing more often than you would the name helium-4. The isotope symbols have 3 parts: the element symbol, the mass number. So like for helium-4, that number 4 right there is the mass. That's where that 4 goes, okay? And then sometimes, not always, but sometimes you'll see this number off to the bottom left. This bottom number is the atomic number. A lot of times this bottom number will not be included. Because it's helium, we can just look on the periodic table and see that helium is number 2. So a lot of times people don't include this atomic number, but you definitely need these 2 parts here, right? You have to know which element it is, and you have to know what the mass number is. So once again, you can write things out this way, or you can write it out this way, the name versus the symbol. Okay, and your all's assignment for me today, which I'm going to explain more of during class, what we're going to be looking at are different isotopes of different elements and trying to determine how many protons, neutrons, and electrons are in those different isotopes. Okay? Thanks for watching, and I'll see you guys in class next time.